Alrighty, welcome back, mathematicians. Now we're on to 3.7, which is all about implicit differentiation. Kind of a title that will be explained later. So far we've kind of only taken the derivative of a function y equals f of x, where y is expressed explicitly in terms of x, aka there's only x involved. So sometimes we're going to encounter different equations where we can't get y alone. Those are called implicit equations, not functions. Remember, these are called equations now. Because we know what a function is. We defined it. So we can have ones that look like y cubed plus x cubed minus 9x y equals 0. We can have y squared minus x equals 0. Or we can have x squared plus y squared minus 25 equals 0. Those are all implicit equations. Basically, I can't get y alone. Alrighty, so I can't get y alone, right? I can't have one side with just y and one side with only x's. So let's look at that second equation right there. Y equal to x squared. Oh, sorry, nope, not that one. Y squared equal to x. And we're going to ask, how can we find dy dx? So basically, if I solve for y right here, I can get y1 equal to the square root of x and y2 equal to the negative square root of x. So if I take the derivative with each of those, I know from power rule, also I know this quick one for square root of x, that dy1 over dy1 over dx equals the square root, 1 over 2 root x, and dy2 over dx equals the negative 1 over 2 root x. Well, those are two equations. So I need to somehow make it into one. So what we're going to do is we are actually going to differentiate both sides with respect to x, treating y as some function of x. Remember how we did that with u last section in chain rule? Kind of something similar. Actually, very similar. So we're going to use the fact that d dx of f of u is equal to f prime of u times du dx. Now just think of it if it was y. Okay? So, since, whoopsies, we're going to have d dx of y squared equal to d dx x. So we're going to get 2y times what? dy dx. So if I think of f of u as u squared, well, I know that derivative is 2u, or in this case 2y, times dy dx, equal to, well, we know the derivative of x is just 1. So this comes from here. And then I want to find dy dx, so when we say solve for, I want that thing that I'm solving for to be equal to everything else on the other side. So I'm going to divide by 2y. I get dy dx equals 1 over 2y. If you go back up here, when y1 equaled the square root of x, I had 1 over 2 square root of x. Well, y1 was square root of x. And here, I had y2 equals the negative square root of x, and so then I had its derivative as negative 1 over 2 root x, and that's the same thing as 1 over 2 y2. So you can see how that connection is made. Okay, so let's do a little trickier one. These kind of make best with practice, and then you can kind of make up a set of rules as we go. So we're going to differentiate x squared plus y squared equal to 25 with respect to x, WRT with respect to. So take the derivative with respect to x of each term, because that's the sum and difference rule. So x squared, I know that's just going to be 2x plus y squared is going to be 2y times dy dx equal to a derivative of constant is just 0. I also like to call y prime dy dx. It just saves me time, it's easier to write, it's faster, and everything's just on one line. I don't have some derivative coming, not derivative, fraction. So if I just call 2x plus 2y y prime equal to 0, I now need to solve for y prime. So I'm going to subtract each side by 2x. So I get 2y y prime equal to 2x. And then I can divide by 2y. So then I get y prime equal to 2x divided by 2y. The 2's cancel out, and I'm just left with x divided by y. Whoopsies. No, I'm not. There's a negative. Careful. I went a little too fast. There we go. Okay. So, not too bad. And then what if I give you a point to find the tangent line, I have to give you x and y. So I can't tell you, oh, when x is 2, because there's 2 y values. Like, this is a circle, right? If I draw this, wow, what is that axis? Looks kind of, what if I move this over? Oh my god, this is so cool, right? So that's our circle. So if I say x equals to 2, well, that's Come on. Yeah, that would be like this point and this point. I have to give you an x and a y. So let me find what point I was supposed to give you. Oh yeah. In this case, it's 3, 4. So I'm going to plug in for y prime. So for, right, this is an xy coordinate, so it's going to be -3 divided by 4. Cha-ching! And we're done. What's the slope at 3, -4? Well, that's going to be -3 over -4 and 3/4. And you can kind of look at like what that tangent line would look like. Right at 3, -4, I am increasing. I have a positive derivative. Act like that is a line. At 3, 4, I'm decreasing. I have a downward pointing derivative. Or tangent, excuse me. Alrighty. So now we kind of know what we need to do just to do implicit differentiation. So we're going to differentiate both sides of the equation. Remember, it's not a function, it's an equation. With respect to x, treating y as a differentiable function of x. All right, and then once we've differentiated, right, we need to solve for dy dx. So how we do that is we collect all the terms that have dy dx and solve then for dy dx. So we're going to collect them all on one side and then solve from there. So far, we've only seen it where they've always been on one side. Alrighty. So, I really like this example. Alrighty. So, find dy dx if y squared equals x squared plus sine x times y. Alrighty. So what's useful for me usually when doing these types of problems is that if I'm taking the derivative of y with respect to x, I'm going to treat it like I would normally and take the derivative. I'm just going to multiply by a y prime every time. So when I'm taking the derivative of y squared, well, I know that that derivative is going to act just like x squared, but I'm just going to multiply by dy dx. Or in my case, I like to write y prime. So let's do it term by term. So we're taking the derivative of y squared, 2y times y prime. X squared we know is just 2x plus, now I have to deal with sine xy. So notice that this is chain rule, right? Sine is my outside function, xy is my inside function. So I'm going to take the derivative of sine and keep xy, my inside, the same. So sine's derivative is cosine. I'm going to keep xy on the inside. And now I'm going to take the derivative of xy. That's x times, we're treating y as a function of x. So this is product rule here, okay? So product rule says I can take the derivative of one and then keep the other one plus vice versa. So let's keep y and take the derivative of x. X's derivative is 1 times y, because we just kept y there. Plus, we're going to keep x, and now we're going to take the derivative of y. What's the derivative of y? It's y prime. We're trying to figure that out. Alrighty? So, I differentiated both sides, and now I need to collect terms of dy dx. So anything that has a dy dx in it, or a y prime, those are the same thing, I need to move to the other side. Note that this x times y prime is multiplied by cosine of x. So it might be helpful to rewrite the equation distributing this cosine of xy. Alrighty, so I have this term with y prime and this term with y prime. So I'm going to subtract x minus cosine xy y prime because it's added here, so the opposite of addition is subtraction. So I'm going to subtract it from both sides. So 2y y prime minus x cosine of xy, that looks like a g, y prime equals to 2x plus y cosine xy. All right, now what are we going to do? So, since the whole point of collecting the terms of x dx dy on one side is so that I can now pull out a y prime from each term. So now I can say that y prime is times 2y minus x cosine xy equal to this stuff again. And since y prime is multiplied by 2y minus x cosine xy, I'm going to need to divide it on both sides. This is really just a test of algebra right now. So we're left with y prime is equal to 2x plus y cosine xy divided by 2y minus x cosine xy. Alrighty? That looks like a lot, but we're done. So what about if we have like higher orders, if I need to take the derivative of this again, right? So in chain rule, when we were taking the derivatives and we were given what were we given? Like if we used u, I need to go back and plug in for u. So if I take the derivative, since I have y's here, I can't get y alone, so I can't plug in y. But if I take the second derivative, I might have y prime somewhere. I can plug that in because I know what y prime is, because I had to solve it first to get y double prime. So what I'm saying is, if we find y double prime, it's kind of a three-step process. Find y prime, find y double prime, and then plug in y prime if we need to. All right, so we're gonna find y double prime for y equal, not y equal, that is a bad habit. 2x cubed minus 3y squared equal to 8. All right. So I know how to do the derivative of 2x cubed. It's going to be 6x squared minus 6y times y prime. And the derivative of a is just 0. Alrighty. I now need to solve for y prime. So I'm going to add 6y prime on each side. So that I get 6x squared equal to 6y prime. Divide by y prime. Sorry, not y prime. Divide by 6y to get y prime alone. And that is not a negative. That's going to confuse me. My 6's cancel out, and I'm left with y prime equals x squared over y. Okay, cool. So I found the first derivative. Step 1 done. Now I need to find the second derivative. All right, so we're going to box this off so we can come back to it later. Well, we're going to use it later, but we're also going to use it right now. So I'm going to take the derivative again, right? The derivative of the first derivative is the second derivative. So now I have x divided by y. So I used product rule earlier. Now I have something, I have x divided by a function of x. So I need to use quotient rule, right? So the derivative of y double prime, sorry, of y prime is y double prime. And quotient rule we know is going to be low d high minus high d low. What's d low? The derivative of y. It's just y prime. Y prime over low squared. I almost said low prime. Alrighty. So then I can simplify. And this is going to be y over 2x divided by y squared minus x squared over y squared y prime. So one of these y's is going to cross out. So we get 2x over y minus x squared y squared times, I know what y prime is. It's x squared over y. And the reason I can write it like this is because y prime is like y prime over 1. And remember how we can move fractions around like that. So alrighty. And then we can simplify again. So we get 2x over y minus x to the 4th over y cubed. Alrighty? So I know I said earlier that you can stop at one point and then you're done, like in simplifying chain rule. Not so much here. This is the final answer. I mean, you could leave it maybe the line above it, not multiplied out, but this bottom line is correct. This third line right here is not enough. You're kind of giving me a half-ass answer where I have to go search for the rest of the answer somewhere else. I don't know what y prime is. I know when I scroll up that it's x squared over y. I need you to tell me that. I need you to give me an answer with only x's and y's in it because that's what the problem gave me. It didn't give me a problem with y primes in it. Okay? That's why I need just x and just y. Sometimes you might be lucky that there's no y primes in the second derivative, so you don't need to plug it back in. That's probably going to be rare. Alrighty, so moving on to the next part. So the tangent line has a little friend. she's named the normal line. And they are perpendicular to each other. Right? So the normal line is 90 degrees to the tangent line. So these are important. Why? The normal line is used a lot in like vector analysis, like matrices and stuff, and like higher dimensions, and a lot in like applied stuff like physics. So, oopsies, there we go. If m is the slope of the tangent, then n equal to -1 over m is the slope of the normal line. Okay? So now we're going to do example 5 in the textbook. It's a really good example. And we're going to use one of those functions that we kind of talked about earlier. So we're asked to find tangent and normal lines to the curve x cubed plus y cubed minus 9xy equal to 0 at 2, 4. Okay? So first we're going to check that 2, 4 is on the curve. We do that by just plugging in. So we're going to have 2 cubed plus 4 cubed minus 9 to, 2, 4. And hopefully that'll equal 0. So that's going to be 8 cubed, not 8 cubed, it's just going to equal 8. And then plus 64 minus 2 times 4 is 8. 8 times 9 is 72. And that deed and that is equals 0. So we're good. So to find the slope of the tangent line, that's the same as the derivative at that point. We've talked about that. So I'm now going to find dy dx at 2, 4. So you guys don't have to put d dx on every term like I do. It's just breaks everything apart so I can focus it one at a time. So I know this is going to be 3x squared plus 3y squared times y prime. Remember, it's really easy to just think about it as if it was x and then just multiply by y prime, Remember, x prime is just 1, so I'm kind of already doing that. So minus 9 times x times y. So that's going to be, I'm going to take the derivative of x and hold y, plus hold x and take the derivative of y. My y's keep looking like g's, and I am sorry. Okay, cool. And the derivative of 0 is just 0. So let's get all of my y primes on one side. So 3x squared plus 3y squared y prime minus 9y plus 9x y prime equals 0. So this guy and this guy are going to move to the other side. So I get 3x squared minus 9y equal to minus 9x y prime minus 3y squared y prime. Right? And then I can simplify to get, not simplify, I'm going to pull out y prime from each term. That's why I collect them all on one side, so then I can pull out a y prime really easily. So I'm going to have y prime times minus 9x minus 3y squared. So then I'll get 3x squared minus 9y divided by negative 9x minus 3y squared equal to y prime. Beautiful. So m, let's call that the slope of the tangent line, is going to equal y prime when I plug in 2 and 4. So 2 is my x value, so I'm going to have 3, 2 squared minus 9 times 4, my y value, over negative 9, what's x? 2 minus 3, oopsies, 4 squared. Okay. So what does that simplify to? 3, 2 squared is 4, so 3 times 4 is 12, minus, wait a second. Okay. Yeah, minus 36. So I think I did something wrong. 1 second. Do you see it? That negative 9 distributed to this negative 9. Haha. Positive, positive. Positive. Okay, great. Not too bad of a fix. Okay. So 3, 4, 12. 12 minus 36 over 18. 4 squared is 16 minus times 3 is 24, so 18 minus 24. And that should equal all right. Okay. Oh, because 3 times 16 is not 24. What I was thinking of, I don't know what I was thinking of. 6 times 4. Okay. 16 times 4 is 32. Yeah, 48. Okay. That's what I wanted. Okay, perfect. So because then I get $30 and what was that? 8, 16, and 10, so 24. Okay, perfect. That's what I want. Okay, sorry about that. The book did it differently than I did. Okay, cool. And that simplifies to 4/5, which is what we wanted. So the tangent line goes through 2, 4, and the slope equals 4/5. So y equal to 4 or 5x plus b, and then we're going to plug in 4 equal to 5 times 2 plus b. And so then I get 4 minus 8/5 equals b, and b equals 12/5. Okay, cool. So then my tangent line is going to be, if I put that all together, y equal to 4 over 5x plus 12 over 5. Oops. That is our beautiful tangent line. We love him. Okay, cool. So what about the normal line? So the normal line goes through 2, 4 as well. They have to intersect each other. And n equals -1 over m, or the reciprocal, right? So it equals -5/4. So y equals -5/4 x plus b. We're going to plug in x and y, so we get 4 equal to -5/4 2 plus b. So then 4 plus 10 over 4 equals b. That's also 5/2, so that's 18. No. 8 plus 5, which is 13. Yeah, so b equals 13/2. So then our normal line is going to equal y -5/4 x plus 13/2. And that's our normal line, just like that. Nothing too scary from finding the tangent line, just you have to manipulate the slope at that point to just define a perpendicular. You're still going through that point though, okay? Hope that's clear. All right, so now we are done with whatever it's called, what,